Hello again. So unfortunately, Srinivas Mogili and Xichen Wang, who really spearheaded this part, couldn't be here. They're in Taiwan. Yeah, without further ado, let's jump into it. Quick overview. I'm going to start again with the motivation behind the tests, talk about the methodology here. Well, I should introduce what we're doing first. That's right. So here I'm going to be talking about how we are estimating the two-way shear strength of these large reinforced pile caps. So I'm going to show the ACI approach, I'm going to show the JSEE approach, and then I'm going to show something called the soft and strut and tie approach, which had very, very good results. So overview, I'm going to talk about the motivation. I'm going to talk about the methodology used here, applying methodology to the current tests, the results of that, and then extensions to other tests with different A/D ratios. And then I'll summarize everything again. So motivation was we had all of these amazing test results from the test program that I just talked about, and we wanted to see how the ACI approach, JSEE approach fared, and if there was a better approach to the conventional strut and tie model, which is what we did, as you were asking about earlier, to design a testing program. So number one question was, do the current ACI JSEE approaches provide reasonable estimates of strength? So are they excessively conservative? Conservative is good, but too conservative and inefficient. Are there alternatives that could provide better estimates? And then do these alternatives fare better for other tests? So maybe they work for our tests, but they don't work for other tests. We wanted to evaluate some other tests as well. And so what I'm showing here on the axis is a normalized measure of unit shear strength relative to the small specimen. And then over here is the effective depth in millimeters, and then inches if you prefer it up here. And this is again a plot made by Srinivas. So here we have the 3-layer specimens. I'm not going to show the 1-layer specimens, but the tendency was similar. And so we have S3ADC here and 3ADC here, and then the L specimens here normalized. And again, we see that there is a reduction in shear strength. And what we have here is the ACI 31819 approach, which is proportional to 2 over the square root of a ratio dealing with the effective depth. This dashed blue line here is the JSEE approach, which is proportional to the chordic root of the ratio of 1 over effective depth. And then here, I'm not going to talk about it, but in the paper written by Srinivas, he proposes an alternative that is closer to what we actually observed. But again, not the subject today. So I'll talk briefly about the soft and strut and tie method. Show of hands, anybody already using this or familiar with this? All right, some familiarity with it. That's okay. That's the intent. Okay. And so Srinivas made this excellent diagram here that walks you through what you would do if you're going to approach this with the soft and strut and tie model. So the first thing you do is you're going to assume a flexural breadth in compression, and that's B sub F here. And this is an iterative process, so you can start really anywhere you want, but if you want to convert it relatively quickly, you can start with this value here. Then you're going to determine the flexural reinforcement ratio based on the amount of reinforcement that crosses the plane that you're assuming, and that's rho sub F. Then you're going to do a sort of classical calculation here to get your neutral axis depth. From there, you'll calculate a shear breadth, which is just B sub C, plus this ratio here. You're going to check if this shear breadth that you calculate is equal to what you had assumed previously as your flexural breadth. And if not, you're going to adjust. You're going to increase or decrease depending on how those two compare to each other. And you're going to go back to the step, and you're just going to keep doing that until they converge. Once those two converge, you're going to calculate the strut capacity. So the idea here, basically, is that you're formulating the question in 2 ways. On one way, you are calculating the breadth of the strut and compression, but you're also assuming that there's sort of a imaginary flexural beam that also runs between those two, and you're iterating until those two converge. That's happening here. So from there, you'll calculate the strut capacity. There's a figure for this in the next slide. But that strut capacity, the area of the strut, is going to be KD, which is your depth times your effective breadth. You just calculate this, and you're going to have an inclination angle associated with that. So again, area based on D to E converged. You're also going to include softening factors here. One of these factors is proportional to the concrete compressive strength. The other factor is proportional to the inclination angle of the strut. And that inclination angle runs back to sort of the centroid of the stress distribution of the top portion in compression. It'll be much clearer on the next slide, but words first. And then from that, you'll calculate the capacity as the sum of the vertical components. So you've got your inclined struts. In our case, you have 3 inclined struts. You'll calculate the compressive capability of those struts. And then using theta, the inclination angle, you'll calculate the vertical contributions and calculate the corresponding ultimate load. And then you'll do a similar thing for that equivalent beam that we have. You'll calculate the capability of that equivalent beam and flexure, and then you'll calculate the contributions from the three parts. So, in pictures, this is what it looks like. So for our tripod specimen, we've got the diameter at the top, we've got the reinforcement crossing here, and again, the flow chart that I showed on the previous slide, what we have here is you're forming a strut that runs from 1/3 of the way below this KD area here to just above the reaction point here. And again, the area of the strut running from here is KD times that effective breadth that you're calculating. And then it also kind of shows you the equivalent beam that we're talking about here. So again, the breadth of that equivalent beam is E sub E, and that's the converged value that is the breadth in flexure equal to the breadth in shear. And so again, you go through this iterative process to do this, and then based on data and then the compressive strength of that strut, you calculate what the total vertical load of P would be. And then you take the minimum value of what that is for flexure versus what that is for shear. So one of the neat things here is that if that value in flexure is smaller than that value in shear, you can also get the yield load that you're expecting for your specimen rather than simply the load associated with the compressive or shear failure. So these are the results for the test that I just presented, the 12 experiments that we conducted. So what's being shown here, the X's are the softened strut and tie method. The black dots are ACI sectional checks. Open white dots are ACI strut and tie checks. And then the triangles are the JSCE checks. So you can see that the ACI methodology, which are all of these up above, is quite conservative, typically on the order of 2x, but in the best of cases, more like 1.6x. So overestimating the strength. The JSCE tended to fare a little bit better, no more than 2x, but down to similar sort of 1.4, 1.6x. The softened strut and tie model fared quite well here. As you can see, it consistently was conservative or very, very accurate. So, lowest ratio about 1.0, highest ratio about 1.5. So quite a bit more accurate here. But that wasn't enough. We wanted to know how it did for other ranges of parameters. So we dug into the literature and found these tests that were conducted by Miguel Portola et al. In 2018. They use different reinforcement ratios. They also use different geometries. So whereas our A over D ratio in the 12 tests that we conducted was 1.0, so the shear span was equal to the effective depth, they actually ranged from 0.84 to 1.68. They were also lightly reinforced, so whereas ours were over-reinforced and had high strength steel, some of theirs were lightly reinforced such that it was possible to have flexural yielding prior to a shear failure. This is just an example of what some of their specimens look like. You can see consistently a single layer of reinforcement. And this is an example showing how we fared in our estimates. So vertical axis here is the test value over the calculated value, so anything over 1.0 is going to be conservative and safe. And then this is the A over D ratio of the specimens. I'm showing two different things here just because the cool thing about the SSTM is that it's possible to hit both. The blue values here are the ultimate load. So you can see once again that the softened strut and tie method was capable of predicting conservative, safe, but not overly conservative values for the ultimate load. So average of about 1.2. And then here is showing the yield load, which is actually quite a bit more nuanced and difficult, but it also did a pretty good job of calculating what the yield load was. So just to summarize everything, it's prudent to provide reasonable yet safe estimates of strength. We want to be safe, obviously, but if we have too high of a factor, then it can lead to inefficient designs. So we always want to be pursuing the most reasonable yet safe approach. The current size effect predictions appear to be over-conservative for very deep members loaded in two-way shear based on this limited number of tests. We obviously do think more tests are always warranted. We did comparisons for 12 new specimens. The SST had an average ratio of measured over predicted of 1.15 with a coefficient of variation of just 11%, so quite tightly bounded. The ACI two-way shear mean ratios were 2.27 with a COD of 20%, so quite a bit more conservative, quite a bit more scattered. The JSCE fared better, about 1.6 with a COD of 11%. The ACI strut and tie method also fared similar to the two-way shear checks. Looking at the Miguel Portola specimens, of which there were 9, they had rebar and size variations, but also fared quite well. So average there of measured over estimated was 1.22 with a COP of just 7%. And that's it. Thank you all for your attention.